Deep beneath the scorched red earth of Western Australia, the Beta Hunt mine stands as a geological marvel, one of the rare places on Earth where both nickel and gold share an uneasy coexistence, trapped within the tortured remnants of an ancient volcanic past. Here, in the heart of the Norseman-Wiluna Greenstone Belt, the echoes of Earth's fiery youth tell a tale of extreme heat, violent tectonic forces, and an alchemy of nature that has left behind a treasure trove of minerals, concealed in rock over 2.7 billion years old. The rugged terrain of Western Australia holds more than just history. It contains a living record of planetary evolution, where each layer of rock tells a story of transformation. The deep underground labyrinth of Beta Hunt is a time capsule of fire, upheaval, and an almost mystical process of mineralization. The unique interplay between magmatic activity, structural deformation, and hydrothermal fluid migration makes Beta Hunt an unparalleled study of nature's ability to concentrate elements into economic deposits. Don't forget to click on that subscribe button, hit the bell icon, and like this video, as it's the best way to support this channel. And if you enjoy it, consider sharing it around. For decades, Beta Hunt was known primarily for its nickel deposits, with gold production remaining a secondary focus. However, in 2018, the world's attention was drawn to a staggering discovery, the Father's Day vein, an extraordinary deposit of specimen gold that defied all expectations. Miners, following a routine excavation, unearthed a slab of quartz dripping with gold. Its surface is encrusted with thousands of ounces of high-purity gold. The discovery yielded over 24,000 ounces in just a few days, including massive gold specimens such as the King Henry nugget, which weighed 90 kilograms and contained over 2,300 ounces of gold. This was a rare bonanza-style deposit, where gold had accumulated in extreme concentrations, likely due to structural traps within shear zones, where gold-bearing fluids had pooled and precipitated in staggering abundance. The Father's Day vein was not an isolated occurrence. It revealed a deeper truth about Beta Hunt, the potential for more hidden pockets of ultra-high-grade gold, concealed within a tangled labyrinth of fractures beneath the mine. As the mine expands and new tunnels are carved into the depths, geologists speculate that additional bonanza-grade deposits may await discovery. The very forces that created the Father's Day vein may have left behind other hidden caches of gold, locked away in the labyrinthine faults and folds of the Beta Hunt ore body. The lure of another world-class discovery keeps miners and geologists driven to push further into the unknown depths of the Earth. The story of Beta Hunt begins in the Archean Eon, a time when Earth was young. Its crust was still forming, and its interior a seething cauldron of molten rock. In this tumultuous world, cometite lava, an ultramafic rock with magnesium levels far beyond anything produced by modern volcanoes, flowed like liquid metal across the seafloor. Unlike today's basaltic lava, which oozes sluggishly from volcanic vents, cometites erupted at temperatures exceeding 1600 degrees Celsius, surging in torrential lava rivers across the primitive crust. Cometite volcanism at Beta Hunt likely occurred in a volcanic arc or back arc basin setting, where mantle plume activity provided the high temperatures necessary for ultramafic magma generation, where mantle upwelling and lithospheric thinning allowed superheated mantle-derived lavas to reach the surface. These initial extensional settings were later overprinted by compressional tectonics, where oceanic crust and volcanic sequences were deformed and thrust together to form the larger greenstone belts we see today. As the lava spread rapidly across the seafloor, it formed expansive lava plains, rather than towering volcanic cones. Unlike modern volcanoes, cometite eruptions did not build steep stratovolcanic edifices. Instead, they produced low-relief volcanic landscapes with extensive lava tubes, sheet flows, and pillow lavas where eruptions occurred underwater. As these blisteringly hot cometite flows surged through submarine channels, they began to erode the softer rocks beneath them. This erosion exposed sulfidic sediments, iron-rich layers that had settled in ancient ocean basins. These sediments would become crucial to what followed, providing the sulfur necessary for one of Earth's great mineralogical transformations, the formation of nickel sulphide deposits. Comatite lavas, as extraordinary as they were, no longer exist on Earth. The conditions necessary to produce them, extremely high mantle temperatures and a unique chemistry, ceased to be a feature of Earth's geology over 2 billion years ago. Since then, the planet has cooled significantly, and the magmatic processes that once allowed for comatite volcanism have disappeared. The ancient flows, preserved in places like Beta Hunt, serve as one of the few remaining records of this long-lost chapter in Earth's volcanic history. In the darkness of ancient underwater valleys, the cooling comatite flows began to lose their ability to retain heavy metals. As their temperatures dropped, nickel, iron, and other base metals crystallized out, sinking like heavy droplets of molten metal into trough-like depressions carved by the lava's erosive power. The rapid cooling of these flows ensured that the heavier elements had only a short window to separate from the silicate melt before they were locked into the rock record. The Norseman Wiluna Greenstone Belt, which hosts the Beta Hunt mine, is a product of a long history of tectonic compression, subduction, and crustal deformation. Originally, this belt was formed through the accumulation of volcanic rocks, including comatites and basalts, in a series of submarine volcanic arcs and back arc basins. Over time, these volcanic sequences were subjected to intense compressional forces, causing them to fold, fault, and stack into thrust sheets. This process, known as crustal shortening, played a crucial role in forming the structural traps that later hosted mineralization. As these volcanic terrains were compressed, they were also intruded by granitic magma, which contributed to regional metamorphism and the remobilization of mineralizing fluids. These fluids, rich in gold and other metals, migrated through the newly formed shear zones and faults, depositing gold in structurally favourable locations. This explains why Beta Hunt contains both comatite-hosted nickel deposits and structurally controlled gold mineralization. Superheated hydrothermal fluids, rich in gold and silica, migrated upward through the Earth, exploiting weaknesses in the rock, shear zones, faults, and pre-existing nickel-rich sulphides. The Lunnon basalt, which lay beneath the comatite flows, became an unexpected host for these migrating gold-bearing fluids. Within its fractures, quartz veins formed, and within these veins, gold precipitated. Over millions of years, this process created extensive shear-hosted gold deposits, where gold lay hidden within quartz carbonate veins, and alongside remnant nickel sulphides. In some places, these hydrothermal fluids found structural traps, where gold could accumulate in staggering concentrations. The incredible pressures deep within the crust forced gold out of solution, causing it to crystallize in rich veins that would remain hidden for eons, waiting to be uncovered by human hands. Beta Hunt is more than just a mine, it is a living relic of Earth's most ancient geological processes. A place where fire and water, heat and pressure, chaos and order have conspired to create something truly extraordinary. And as long as its tunnels reach deeper, the mystery of Beta Hunt will continue to unfold, revealing more secrets locked away in the stone of time itself. I hope you found this as interesting as I did, and as always, thanks for watching. The Cannington silver-lead-zinc deposit stands as one of the most extraordinary geological marvels of the modern mining world. Hidden beneath the ancient landscapes of the Mount Isa inlier, it holds within its depths a rich history of formation, transformation, and enrichment that spans over 1 billion years. Situated within the eastern succession of this Proterozoic terrain, Cannington is considered one of the richest silver deposits in the world due to its extraordinarily high-grade silver content in comparison to most other polymetallic deposits. The ore boasts an average silver grade of approximately 538 grams per tonne of crushed ore, making it exceptionally silver-rich relative to typical base metal deposits. In some zones, silver concentrations can be even higher, particularly where late-stage hydrothermal fluids have further enriched the system. This astonishing silver grade, coupled with a significant lead concentration of 11.6% and zinc concentrations of 4.4%, results in an incredibly profitable and high-value ore body. Don't forget to click on that subscribe button, hit the bell icon, and like this video, as it's the best way to support this channel. And if you enjoy it, consider sharing it around. Born in the fire of tectonic upheaval and bathed in the crucible of time, Cannington's story begins over 1.6 billion years ago, in a world starkly different from our own. The Earth was a restless and volatile sphere, its crust stretching and fracturing as deep-seated forces pulled at its foundations. The Mount Isa region lay at the heart of an ancient rifting event, where vast sedimentary basins formed in response to powerful extensional forces. This was a realm of rising and falling oceans, of shifting continents, of colossal fault systems that ripped apart the land. This was the breakup of the supercontinent Nuna. Within these basins, mineral-laden fluids seep through the fractures, mingling with sediments rich in iron, manganese, and carbonate. Over time, these fluids laid the foundation of what would become one of the richest silver-lead-zinc deposits known to humankind. The primeval world that fostered Cannington was one of transformation. As the Earth's plates continued their inexorable dance, the basin that hosted this mineralization was buried, compressed, and heated to unimaginable extremes. The slow, patient alchemy of metamorphism gripped the rocks, forcing their atoms into new arrangements, transmuting simple sediments into a complex tapestry of gneisses, quartzites, schists, and amphibolites. Under this immense pressure and heat, the original sulphide-rich mineralization was not merely preserved, it was reforged, its textures erased and rewritten by the forces of nature. Yet even this metamorphic baptism was not the end of Cannington's odyssey. The relentless movements of the crust twisted and folded the deposit, creating sweeping, isoclinal folds that repeated and concentrated the ore. A great structural symphony unfolded over millions of years, where ductile strain wove ore lenses into sinuous patterns, while brittle deformation shattered and displaced the mineralized zones. These dramatic shifts, dictated by the unseen power of geodynamic forces, created the complex geometry that modern miners now endeavour to decipher and extract. While Cannington today is regarded as a Broken Hill type deposit, and I've made a video on Broken Hill, you can find a link to that in the description down below, its origins are far more enigmatic. Geological evidence suggests that it may have started as a sedimentary exhalative deposit, or a SEDEX deposit, where metal-rich hydrothermal fluids vented onto the seafloor, mingling with fine sediments in an ancient anoxic ocean basin. This process, occurring over thousands of years, led to the accumulation of vast quantities of zinc, lead, and silver in fine layers of sulphide minerals. These early sulphide deposits, rich in galena and sphalerite, lay hidden beneath deep waters, slowly buried by accumulating sediments over millions of years. However, unlike many SEDEX deposits that remained relatively untouched by tectonic forces, Cannington was later subjected to intense metamorphism, obliterating much of its original texture and remobilizing its metals into the strata-bound, high-grade ore lenses we see today. As mentioned before, the formation of Cannington is closely linked to the breakup of the ancient supercontinent Nuna, an event that profoundly reshaped the geodynamics of the Proterozoic world. During this period, extensive crustal extension and rifting led to the development of deep sedimentary basins that would later become the repository for the metal-rich hydrothermal fluids that formed the initial SEDEX-style mineralization. As Nuna fragmented, the resulting tectonic stresses triggered widespread metamorphism and deformation, remobilizing the original sulphide deposits and enhancing their grade through structural repetition and fluid-driven enrichment. This prolonged sequence of geological events transformed a once-buried mineral system into the world-class silver-lead-zinc deposit that Cannington is today. The process of silver, lead and zinc deposition in such profound numbers is a story of immense geological precision. The initial SEDEX-style mineralization concentrated metals from deep in the Earth's crust into a confined basin where reducing conditions allowed sulphides to precipitate out of solution. But it was the later metamorphic transformation that elevated Cannington to its current status as one of the world's richest silver deposits. Heat and pressure recrystallized the sulphides, increasing their grain size and forming dense, concentrated ore shoots. Additionally, later hydrothermal fluids, driven by deep-seated tectonic activity, enriched the system further, introducing more silver and rare minerals like fribegite. The combination of an exceptional primary ore-forming process with this later metamorphic and metasomatic refinement resulted in a deposit of staggering richness and complexity. But what truly sets Cannington apart from other deposits of its kind is the process of post-metamorphic metasomatism that further enriched its ores. As tectonic activity waned and cooler fluids infiltrated the system, these chemical messengers carried elements that refined and enhanced the existing mineralization. Fluorite, magnetite, Hedenbergite, and pyroxmangite were introduced, forming stunning mineral assemblages that provide invaluable clues to the geological history of this remarkable deposit. Silver, already present in abundance, was further concentrated by these late-stage hydrothermal overprints, rendering Cannington one of the most silver-rich deposits on Earth. This enrichment was so profound that even among the world's greatest Broken Hill-type deposits, Cannington wealth in silver remains unparalleled, an almost poetic combination of eons of mineralogical refinement. The deposit's final shaping occurred as brittle faults sliced through the ore body, dividing it into the northern and southern zones that today guide modern extraction. The Trapel Fault Zone, a stark reminder of the Earth's enduring dynamism, cleaved the system, creating the structural complexities that make mining Cannington a formidable yet rewarding endeavour. With the final touch of nature's sculpting hand, the deposit was buried beneath the sands of time, concealed under layers of Cretaceous and recent sediments. For millions of years it lay undiscovered, hidden beneath the surface, waiting for the keen eyes and innovative minds of geologists to unveil its secrets. The discovery of Cannington in 1990 was the culmination of relentless pursuit. Geophysicists scoured the land with aeromagnetic surveys, seeking the whispering hints of mineralization buried far below. When drilling finally intersected its ores, it was as if a new chapter of Earth's history had been revealed. What followed was an unprecedented exploration and mining effort that saw this once forgotten rock emerge as the world's largest silver producer. Today, Cannington stands as a beacon of what is possible when the mysteries of deep time are unravelled, when the patience of geological processes meets the determination of human endeavour. Recent petrophysical studies have shown that the deposit exhibits strong magnetic susceptibility due to the presence of abundant magnetite, differentiating it from many classic SEDEX systems. This distinct magnetic signature played a pivotal role in its discovery, as airborne geophysical surveys detected an isolated anomaly, prompting the first drill tests. Furthermore, geochemical analysis of the ores indicates a significant variation in lead-zinc ratios between the northern and southern zones, which correlates with differences in structural strain and fluid flow history. These insights not only enhance the understanding of Cannington's complex genesis, but also aid in refining exploration models for similar deposits concealed beneath thick sedimentary cover. To understand Cannington is to glimpse the grand narrative of our planet's evolution, to see in its rocks the echoes of ancient oceans, the scars of tectonic battles, the whispers of hydrothermal flows. It is a place where the story of Earth's past is written in mineral and stone, a chronicle of metamorphism, deformation, and enrichment that has left behind one of the most treasured mineral endowments of our time. It is a geological marvel, an economic powerhouse, and above all, a reminder that the Earth, in its ceaseless transformation, is the ultimate architect of riches beyond imagining. I hope you found this as interesting as I did, and as always, thanks for watching. Beneath the arid plains of far western New South Wales, in Australia, lies a treasure forged in the crucible of deep time. The Broken Hill deposit, the world's largest accumulation of lead, zinc, and silver, is not merely a mineral deposit, It is the product of cataclysmic forces, ancient oceans, volcanic fire, and a wrenching breakup of one of Earth's earliest supercontinents. To understand Broken Hill is to step back 1.7 billion years into a world vastly different from today, a world of tectonic upheaval, volcanic outbursts, and primal seas brimming with the raw ingredients of life and industry. The story of Broken Hill begins with the assembly of Nuna, one of Earth's first supercontinents, a vast landmass that brought together the ancient cratons of the Earth into a tectonic embrace. Nuna formed between 2 and 1.8 billion years ago, a behemoth of rock and fire drifting across a nascent planet. Yet even as Nuna coalesced, it was doomed to fracture. By 1.75 to 1.6 billion years ago, tectonic forces pulled at the seams of the supercontinent, stretching the crust like a great tectonic drumhead. Rifts yawned open, creating deep basins flooded by primordial seeds. One such basin formed in what is now the Curnamona province, a low-lying marine trough on the margins of Nuna, filled with sediment and bathed in volcanic heat. This was the stage for the birth of the Broken Hill ores. Don't forget to click on that subscribe button, hit the bell icon, and like this video, as it's the best way to support this channel, and if you enjoy it, consider sharing it around. In the heart of the rifted basin, volcanic activity was rampant. Bimodal volcanism, both basaltic and rhyolitic, spewed magma into the waters, forming vast lava flows and underwater calderas. Along with this fiery upheaval came the slow, seeping breath of the deep earth, hydrothermal vents, black smokers that exhaled metal-laden fluids into the seawater. These plumes carried lead, zinc, silver and iron, which precipitated onto the seafloor, settling in fine shimmering layers of sulphides. This process, known as sedimentary exhalative mineralization, or SEDEX, is visually striking. Black smokers, towering hydrothermal chimneys, spewed superheated mineral-rich fluids into the cold ocean water. As these fluids mixed with seawater, dissolved metals precipitated as fine-grained sulphides, which accumulated over time in layers, forming vast mineral-rich deposits. The seafloor in these zones would have been covered in shimmering black and grey sulphide sediments, interbedded with iron-rich cherts and carbonates. Occasionally, hydrothermal mounds would have formed, acting as localized metal traps where higher concentrations of lead and zinc developed. At this time, the Curnamona Basin was an anoxic or oxygen-poor sea, perfect for the preservation of sulphides. Bacteria thrived in the depths, their metabolic activity helping to catalyze the precipitation of metals into the sea floor. Over time, these layers built up into an enormous accumulation, hundreds of millions of tons of lead, zinc and silver-rich sulphides, a colossal ore body lying in wait beneath the waves. However, while SEDEX processes played a major role in forming the Broken Hill deposit, it is not a pure SEDEX deposit. The mineralization has also been influenced by hydrothermal remobilization and metamorphic processes. The intense heat and pressure of subsequent tectonic events caused the original SEDEX sulphides to be deformed, recrystallized, and enriched in certain zones, leading to the formation of high-grade ore lenses. These metamorphic changes set Broken Hill apart from many classic SEDEX deposits, making it a hybrid system incorporating both exhalative and structurally controlled mineralization. Additional evidence suggests that later hydrothermal fluids introduced new elements into the deposit, including gold, bismuth and antimony. These late-stage fluids, likely activated during deformation events, altered parts of the ore body and contributed to further metal enrichment. This multi-stage history explains why Broken Hill remains one of the highest grade base metal deposits in the world. The volcanic activity that fueled Broken Hill's genesis was unlike the towering stratovolcanoes on land. Instead, the landscape would have been dominated by submarine shield volcanoes, fissure eruptions, and hydrothermal vent systems. While these volcanoes did not form the deposit directly, they acted as conduits for metal-bearing fluids and sources of geothermal energy, driving the SEDEX mineralization process. For nearly 100 million years, the Broken Hill sulphides lay buried beneath younger sediments, seemingly frozen in time. But geology is never still. Around 1.6 to 1.58 billion years ago, the tectonic forces acting on the Curnamona province shifted dramatically. After a long period of rifting and basin formation, during which the Broken Hill deposit initially formed, the region experienced a transition from extensional to compressional tectonics. This shift marked the onset of the Illyrian orogeny, a mountain-building event that subjected the crust to intense heat and pressure. Instead of landmasses continuing to pull apart, parts of the ancient crust were now being squeezed together, causing deformation, folding, and deep burial of the Broken Hill ore body. The immense pressure and high temperatures of this event recrystallized the original SEDEX sulphides, transforming them into a structurally remobilized, high-grade metamorphic ore deposit. Pressures reached staggering levels, and the temperatures soared into the granulite facies, over 800 degrees Celsius, metamorphosing the sulphides into coarse-grained, banded ore bodies. Lead and zinc recrystallized into galena and sphalerite. The deposit was no longer a simple SEDEX accumulation. It had now been transformed into something new, a remobilized high-grade lode deposit. Its ores now concentrated into tightly folded, lens-shaped masses within the Broken Hill group. Starting an online store can feel overwhelming, but with Odoo, you can launch your e-commerce business in just 4 simple steps. No coding, no hassle, just an intuitive AI-powered setup that makes everything easy. First, Odoo's website configurator guides you through the setup. Choose your industry, select your colors, pick your features, and let AI generate the structure for you. Then it's just a matter of dragging and dropping your text, images, and branding into place. Want a professional looking store without hiring a developer? This is how you do it. Next, adding products is effortless. Just click New, then click Products, enter the name and price, add a picture, and it's live. Want to enhance it? Upload product images, write a description, and customize the layout with drag and drop content blocks. Even better, if you have a barcode, just scan it and Odoo fetches product details online automatically. Now let's make sure customers can actually buy from you. Odoo integrates with major payment providers like Stripe and supports shipping carriers like Australia Post, DHL, and FedEx. Just configure your payment and delivery options and you're ready to start making sales. Plus, invoicing is built in, so you don't have to worry about setting up a separate billing software. And that's it, your e-commerce site is up and running. Odoo gives you your first app free for life, with unlimited hosting and support. That means you can start selling without worrying about monthly costs. Plus, as your business grows, Odoo grows with you. Add new apps anytime for inventory, accounting, marketing, and more. So if you're ready to launch your online store without the headaches, check out Odoo today. Your website, invoicing, payments, and shipping all in one place, starting for free. Thank you Odoo for sponsoring this video. For over 1.5 billion years, the Broken Hill deposit has endured. It has been buried and unburied, shattered by faults, and warped by additional tectonic forces. Yet, through it all, the ore deposit has remained intact. Today, the deposit lies along the Morkay Shear Zone, a fault system that has subtly reshaped its structure but failed to erase its riches. Mining at Broken Hill began in the 1880s, revealing the incredible wealth locked within the ancient rocks. Even now, geologists continue to study its secrets, using modern exploration techniques to find similar deposits across Australia and the world. As erosion and tectonic uplift exposed the mineral-rich formations of Broken Hill, it became a beacon for human discovery. The interplay between rifting, volcanism, and metamorphic processes has allowed modern geologists to piece together a history spanning nearly 2 billion years. Each layer of rock preserves a fragment of the past, and the study of Broken Hill has also provided insights into mineral exploration across the world. By understanding the conditions that led to its formation, geologists can identify similar settings in other regions, offering clues to untapped deposits that may yet be discovered. The lessons learned from Broken Hill extend beyond its physical boundaries, influencing resource extraction strategies on a global scale. Recent studies have revealed that the Broken Hill ore body exhibits unique isotopic signatures, distinguishing it from other SEDEX deposits worldwide. The presence of distinctive lead isotope ratios suggests that the metals originated from deep within the Earth's mantle, further supporting the role of early tectonic activity in driving hydrothermal circulation. These findings challenge previous models and provide new insights into the deposit's formation. Additionally, geophysical investigations have identified concealed extensions of the ore body beneath younger cover sequences. Advanced seismic imaging and gravity surveys indicate that similar mineralized structures could remain hidden beneath thick layers of sediment, offering potential for future discoveries. The geological complexity of Broken Hill has also influenced the classification of related deposits globally. Some researchers argue that its extreme metamorphic overprint distinguishes it from conventional SEDEX deposits, positioning it within a unique category of high-grade metamorphosed mineral systems. Studies have also shown that the deposit's structural history played a critical role in preserving its economic viability. Unlike many other ancient mineral deposits that have been eroded or extensively deformed beyond recognition, Broken Hill remains shielded by the surrounding metamorphic terrains. This natural preservation allowed for the retention of high-grade ores, making it one of the richest mining districts in the world to this day. So even as mining continues to extract its wealth, the true value of Broken Hill lies in its geological story. It is a living record of the Earth's evolution, a reminder of the planet's ability to shape and reshape itself over eons. Through the lens of geology, Broken Hill stands as a symbol of time, transformation, and the untold mysteries still hidden beneath our feet. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.